Okay, so here's the write-up for the next assignment. And as you can see, we're going to take the Palantiri app that we've been using as a running example and do some more things with it. A lot of this is, part of this is going to look very much like assignment, let's see, I guess it would be assignment 2B, I think. It's just going to use async tasks. So you can reuse most of that code with a few tweaks that we'll talk about in a second. And the main thing we'll do that are different is that this time we'll be using an executor service. Instead of making a thread pool executor, use an executor service that uses a cache thread pool. So that'll give you a chance to work with cache thread pool. It's very simple. In fact, it's probably easier than what you did before, but it just so you get a little chance to play with that. You'll also be using barrier synchronizers. In particular, you'll be using countdown latch and cyclic barrier. If I could spell it right, there's no E, it's cyclic barrier. I'll fix that. And we'll talk about those on Wednesday, so you'll learn how barrier synchronizers work. And then you'll also use a concurrent hash map to implement the Palantiri manager synchronization portion. You'll also use your fair semaphore, which you'll have done for this assignment. You'll just have finished. So just copy that over and reuse it, make sure it works. And so we'll basically be doing those new things. There's videos on all this stuff that you can watch, and of course we'll talk about this in class as well, but start watching the videos. There's really two pieces you'll have to work on. The actual code here is pretty short because you're reusing a large amount of your previous solution with the async tasks. You're just going to change a few pieces of it. So it shouldn't be that hard to do, but it'll take a while to figure out how simple it is to do if you have to learn some new things. So you'll basically update the Palantiri presenter and being async tasks, and we'll look at that in a second. You can reuse a lot of your stuff with changes to meet the new requirements, like the executor service and the barrier synchronizers. And then you'll have to implement the Palantiri manager. Once again, you can reuse your fair semaphore, so that should be straightforward. And you'll have to use a concurrent hash map. Concurrent hash map is a really interesting thing when used in this particular case, and I'll talk about that when we talk about the code. It's a little bit subtler than you might expect. And the grad students get to do everything except they also need to use the Java 8 features. Your undergrads are welcome to do that, of course, too. So let's go take a look at the skeletons. Come over here. A lot of this stuff will look very familiar. Let's take a look at the model layer first. So you'll have your fair semaphore where you just fill in the various pieces that you need. That should be easy, just basically copying it over from before. Here is the Palantiri manager part. So you'll be using your fair semaphore. That should be straightforward. And you'll be using your concurrent hash map, or a concurrent hash map. The Palantiri manager constructor is going to look pretty much the same as before, except you're using the hash map, not the concurrent hash map, not the hash map. Release will also look very much like what you did before. Acquire is the part that's kind of interesting. And for both release and acquire, do not use any explicit synchronization. No synchronize this or anything. All the synchronization is going to be handled by the concurrent hash map. And this is a really interesting use case of concurrent hash map. And it's basically, under the hood, it's using a compare and swap mechanism to make it super fast. So, like I said, release should look very similar to what you did before, except there should be no synchronized statements in this method. So no explicit synchronization, just the hash map, which knows how to synchronize itself, concurrent hash map. Up here is where it gets kind of fun. So it turns out that hash map has a method in it, concurrent hash map, has a method in it called replace. And the way it works is there's a 3-parameter version of replace. And what you do is you basically give it the thing that you want to, the value, and you basically say, if the value equals this, for this key, if the value currently equals this value, replace it with this other value. So what the heck is that going to do? So it's, again, it's 3-parameter version of replace. And so you'll give it the key, which is the Palantir, and so you'll have to loop through every item in the Palantiri set. And what you're going to do is you're going to replace it. If it's true, you'll replace it with false. What the heck does that mean? Well, keep in mind that we use the Palantiri hash map in order to be able to keep track of which Palantiri are available. So true means that the Palantiri is available, right? And so as a result, what you want to do is you want to say, if this Palantiri has a value of true, atomically replace it with the value false. That's what replace does when you use an atomic on a concurrent hash map. And that's essentially a compare and swap operation. So it doesn't, it's very fast, and if there's no contention, it's really fast. But here's the thing, this is really subtle. So you're going to loop from beginning to end of the Palantiri set, checking to see whether or not you can replace a true with a false. Okay, that seems pretty simple. No need to synchronize at a higher level. But there's one rather tricky, subtle thing here. So because that's the only synchronization you have, checking to see whether the value is true or false, you have no other way of locking other threads out from that critical section. And so as a result, it's possible, and I'll let you think about this, it's a very subtle case, where you could have many threads adding and removing things from this concurrent hash map at the same time, where when you start searching in the list, oh, by the way, by the time you can actually start searching in the list, you know that there's at least one item in there. And the reason you know that is because the semaphore is being used to keep account of the number of items that are available. So you don't get to run until you've acquired the semaphore, right? So at that point, when you get through the semaphore, you know there's at least one item in there that's available. But because there could be multiple threads doing this stuff, as you do a search from left to right through the hash map, it might turn out that another thread would come along, and for whatever strange reason having to do with the non-determinism concurrency, it would get a chance to steal your slot before you could get it. So as you're marching along through this thing, there could have been an open slot over here. You start at the beginning, marching through, and before you can find the one that you thought you would get, someone else has come along, because there's no other locking, and that thread grabs it. But another thread might have released one of the slots before where you've already looked, where it was previously true, false, now it's true. So what happens when you reach the end, if you just do a single linear pass to this thing, you won't find the empty slot, even though there is one there. So the trick, it's actually a very simple trick, is you simply use a forever loop. You know what a forever loop is? You just say for, open paren, semicolon, semicolon, close paren, right? So that's forever. Loop forever, and then you go and you do the loop that looks through the Palantiri, basically key set or whatever. You go through the thing, and use the replace mechanism. Now, you will eventually you will converge because there is an item there. This is one of the issues of, you could get into a live lock situation where it might take several iterations to converge. But you will eventually converge because there is something available. Yeah? Is there any reason you use a forever loop as opposed to just a while loop? No, you can use a while true loop, same thing. It's just arguably a little bit more clear. While true and forever are the same thing. And the compiler optimizer should turn them into the same, basically keep going instruction. So that's the subtlety there. You can't loop just a single time, even though that'll usually work. You need to loop until you've actually got an item, and you may have to start over again. So that's the subtlety there. But the concurrent hash map solution is really simple and super fast and scales up really nicely. Okay, so that's basically the model part. Let's go look at the presenter part. So the being async task will look very similar to before with two important differences. We're going to have a cyclic barrier that's used as an entry barrier and a countdown latch that's used as an exit barrier. And we'll talk through those things on Wednesday, of course. And so a lot of the stuff will be the same. The main difference is you'll have to put the right call in here to use one of the barriers to enter the barrier. You'll have to change that. The other stuff is basically more or less what you did before, where you have to make tweaks and so on to add in the calls that will visualize things. That's more or less what you had before. And then down here in on post execute, you're also going to have to use the exit barrier to say I'm finished. So before you start to run, you have to use the entry barrier to make sure that all the threads are up and running before they can all advance. That uses a so-called cyclic barrier. And when you're finished running your iterations, your gazing iterations, then in on post execute, you're going to basically release the exit barrier, which will eventually allow the main waiting thread to continue. And on cancel, it has to do the same thing, but the solution here is easy. Just have on cancel call on post execute. So do the actual work with the exit barrier and on post execute, and then have on cancel call it. So that should be fine. Other than that, that code looks more or less the same. Palantir presenter, you have to fill in the thread factory. You've done that before. That should be easy. And you'll need to go ahead and initialize the entry barrier and the exit barrier. That takes a little bit of thought to figure out what the right value should be for that. The entry barrier will be a thing called a cyclic barrier. The exit barrier will be a countdown latch. We could have used the cyclic barrier for the exit barrier as well, but I just wanted to give you a chance to practice with both. And those things are going to be used to coordinate the threads so that they all start together and that the main thread waits for all the threads to complete before it continues. We'll see where that gets done. So that's basically that logic. Then down here we have begin being tasks gazing. That will be similar to what you did before with the following differences. What I want you to do here is I want you to use the executors, with an S at the end, the executors class, which is a static utility class, and use the factory method that makes a new cache thread pool. So you'll make a new cache thread pool, and that's what you're going to end up passing to execute on the executor. You'll pass that type of pool, a cache thread pool, just to get a little bit of practice with that. And the second thing is that students taking the class for grad credit should use Java 8 streams to generate the being task. And I'll talk a bit more about that. It's a really cool little idiom that I love to use, where you use a method called stream.generate, which will generate an infinite stream, which you then limit to the number of things you want to generate, which in this case is going to be the being count. And you then stick that into a list. It's a really cool little idiom. We'll see lots of examples of that later. I'll talk about it next time. So otherwise, you can just use a regular list if you're an undergrad. And then over here, in the wait for being tasks to finish method, that's the thing that's going to wait for everything. We create a thread that runs in the background, and the Lambda expression of the thread will use the various barriers to wait for all the things to be up and running before they all start. That's a cyclic barrier. And then we're going to wait for all the being tasks to stop gazing. That'll be a countdown latch. So this guy will wait for that. And then you'll have to shut down the executor service when you're done, just so it'll clean out all the threads. That's easy to do. I think you've done that before. Okay, so that's basically what the next assignment is. It's really not that complicated, but you'll have to learn about these other mechanisms. And so we'll talk about them, take a look at the videos, and we'll cover this starting next class.